I've tried talking about this 3 or 4 different ways across the course of my classes today, and nobody seems to appreciate it. I don't really care if you appreciate this. You have to do this right, though. And you can't get the free body diagram for inclined planes wrong. You need to nail that. So I want you to imagine for a moment the back of a pickup truck, perhaps, or a flatbed truck. Okay, so there we go. The box, you want to lift the box, put it in the back of the truck. If you are just going to lift the box to the back of the truck, then you would have to apply a force upwards that is equivalent to the weight of the box downwards. So you understand why that has to be true. If you don't, now's the time to bring it up. I don't need to accelerate the box, so I don't have to lift with more weight or lift with a force greater than the weight. If I just want the box to move upward at a constant speed, then I need to apply a force that is equivalent to the weight of the box, so that my upward applied force minus the weight of the box equals 0. This is the minimum force I have to apply to lift the box. This kind of phrasing I want you to listen for. The minimum force I have to apply to lift the box to get the box into the back of the truck is merely the weight of the box. Is everybody following along with my argument? Give me eye contact and show me, yes, Mr. Sheldon, I understand what you're saying. If I lift more than that, then the box is accelerating. I'm doing more than I have to. But at minimum, I just need to get it started and set it on the back of the truck. But I do have to lift the entire weight of the box. So I can only load this box into the truck if I can lift the box. There's other ways of putting the box in the truck. One way to put the box in the truck is to use something that might assist me in putting the box in the truck. I could use a ramp. A ramp is a simple machine, and simple machines can be used to reduce the force you have to apply to do the same task. There are 4 simple machines, and through my entire course of the day, I have found that not many people know the 4 simple machines. I am sure a handful of you know the 4 simple machines. Can somebody name a simple machine? A pulley is a simple machine. Is there another one? I just named one. Yeah? A ramp. Yeah, we'll say inclined plane. Although I will not say who said this, but they eat lunch in my room. Somebody goes, as another alternative, a declined plane, to which I laughed greatly. And I said, no, they're all inclined planes. We don't call them declined planes. But there are 2 other simple machines. Do we know them? Yep. Yep. You say lever, I say lever, but yes, it applies leverage. One more? Oh, well. These are the 4 simple machines. There are lots of machines in the world, but these are the 4 simple machines. Most machines get leverage by using one of the simple machines as a process. So even a huge crane, designed to build a skyscraper, generally has an advanced pulley system and an advanced lever system, and often a wheel and axle system. But ultimately, all of these simple machines do the same thing. They all exchange force for distance. That's what they do. So you can lift the box straight up and put it in the back of the truck. That's the least distance you would have to travel in order to get the box into the back of the truck. But that will require the most amount of force because you'll have to lift the entire weight of the box. If I want to get the box into the truck by using a ramp, then I will be pushing the box up the ramp using a percentage of the weight of the box. In fact, if I want to move the box at a constant velocity up the ramp, you're in a position now to tell me how much force would be required to do so. You know how to do this problem. I want you to do this problem, like not in the abstract. Like assume for right now that this is a smooth ramp. Here's where I'm applying the rules from yesterday to indicate there will be no friction on the ramp. Libby. So this is a smooth ramp. I'd like you to take a moment and tell me how much force would I have to apply to move the box up the ramp. Now, I'm doing this problem with you, and this is for the benefit of people who have never had physics before and really need this to be done explicitly. I want you to have I only have to lift the box to there. If I want to use the ramp, I have to lift it all the way up there. I got to go a lot further. But if you're loading boxes from your house, which is back there, you're still walking the same distance probably, right? So ramps are there to remove the amount of force necessary to lift something to a different height at the expense of having to go a bigger distance. There's lots of ways that an inclined plane can be made. This is just one. If you take an inclined plane and wrap it around an axle, you get a screw. A screw is an inclined plane that's been rolled. So the idea of a screw is that you have to go around a lot of times to go a very small distance into a piece of wood, but it can put a lot of leverage there. You can put a lot of force on that screw getting into the wood by applying a small amount of force around the outside. All hand tools are leveraging this idea of a simple machine. Pliers are clear levers. Lots of stuff ends up being inclined planes or some version of an inclined plane. And you combine several of these things together and you get like a screwdriver. Like a screwdriver is a wheel and axle with a bit that's designed to push a inclined plane into a wall. And it's a lever because the handle's really wide compared to how small the axle is, giving you leverage over your ability to turn the screwdriver. So all of these are simple machines. But I want you to understand the inclined plane. Do we all have an idea of what I mean by an inclined plane now? Good. So now you have to prove it. So I have a new situation. I have a box on a ramp, and the entire ramp is inclined 30 degrees. The box has a mass of 20 kilograms and is stationary. Okay. What is the size of the frictional force? And what is the size of the normal force? You follow this procedure, use what you've been taught, and you should be able to tell me that the frictional force is 100 newtons and the normal force is 173 newtons. Do the math and show me that these are the right answers. Free body diagram, that's what I want to see. I want to see a free body diagram, breaking up your weight into the components, all that stuff. Did we start with a free body diagram like I asked? Which would be, I believe, three forces: a downward force indicating the weight of the object, a force directed perpendicular to the ramp to act as the normal force of the object, and a force up the ramp that would be the friction acting on the object. Is that what you guys did? I hope. Did you then apply a coordinate system starting with the normal force so you could identify where the angle goes first? Good, I hope so. And then draw in our other coordinate. Like so. Did we recognize that the weight's going to be broken up into weight cosine 30 degrees and weight sine 30 degrees? I hope so, because that means net force in the x direction is weight sine 30 minus friction equals 0. And in the y direction, It's normal force minus weight cosine 30 equals 0. The weight is 200, right? 200 newtons. Okay. Separate thing in your notes where you are careful to walk through the inclined plane and its forces. So I'm going to try and redraw what we have over there. The inclined plane is predicated on the idea that we are inclining our surface. Now, the forces on an inclined plane are pretty straightforward. I'm going to draw them right here on the plane. I'm going to try and draw them a little bit big as day so you can get an idea of how to deal with this, because the biggest problem I've seen is how to deal with the components that you're going to get for an inclined plane. So the first thing I want to remind you about is that when we start doing this, we start by identifying the forces that are acting on our object, and that begins with dealing with the weight of the object. There is, however, a normal force that's acting on the object due to the ramp. I have to draw that perpendicular to the ramp. And then, of course, there's the force I'm going to apply. That's me pushing on the box. I'm probably going to push on the box this way to get the box to go up the ramp. This is my applied force. Remember, we said it's moving at constant velocity. So the net force is equal to 0. Now, here's where I want to stop you. I don't care so much right now about the applied force and the normal force. I care about the weight. And the reason I care about it is because that's the one that's going to be broken up into components. We're going to try and identify a coordinate system that works best here. And to do so, we're going to draw in an x and a y axis. Listen carefully, folks. If you want to get the angle right, I think you should figure it out using, similar triangles and stuff like that and all those rules. But I'm going to tell you how to do it without having to work that hard at it. So I would give yourself this information in your notes. If you want to get the angle right, draw the vertical axis first through the normal force. If you want to get the angle right, draw the vertical axis first through the normal force. Before you draw anything else, identify the angle between the weight and the axis you just drew. That's theta. So I'll say it again. If you want to get the angle right, draw in the axis that goes to the normal force first. And then identify the angle between that axis and the weight. This is only for inclined planes. Only for inclined planes, and only if you're going to set your axis up lined up with the normal force. But trust me when I say, I've been grading these all day, and over half of the folks who got saddled with the inclined plane problem drew their angle in the wrong place. Now, it doesn't matter where you call these the x or the y axis, that part is immaterial. You want to make sure the one that's aligned with the normal force is the one that gets the angle, because I've seen all day people choosing this angle for theta. And this example that I've drawn, I've exaggerated it so much it should be obvious which one is which. But when you start getting those up at like 40 degrees, they all look the same, especially in your drawings where you're not measuring it with a protractor. You follow what I'm saying? So draw in the one that's aligned with the normal force first, draw in that angle next. Then, the next biggest mistake I've seen is people saying, okay, I'm ready to deal with my components, so I'm going to draw in this. There's my components. That is wrong too. The right angle does not go here. Not at all. Whenever we've drawn in components, the vector that we are dealing with is the hypotenuse. So I draw the right angle against the axis, always. But because it's on its side, people go crazy and do it all wrong. So look, your paper allows for you to just do this. If you have to, turn the x-axis so it's horizontal. That will make the picture look better for you and help you draw in your components better. So you can say, okay, there's the first one and there's the second one. Yay, I did a great job. Please, you have one really good chance now to get this right. Let's make sure we have a nice, clear picture in our notes now. So if you have to, just turn your paper so the X is horizontal. Now, the next part of this, look, some of you still, with all of that, will refuse to do this correctly. For an inclined plane, you could memorize that this is going to be the weight times the sine of the angle, and this is going to be the weight times the cosine of the angle. You could memorize that. That the one that's into the plane is weight cosine theta, and the one that's down the plane is weight sine theta. Good so far? Everybody following along okay? All right. Now we apply our rules here, and net force in the x direction equals 0. So that means my applied force has to equal weight sine theta. And also means that my normal force is going to be weight cosine theta. That's me taking net force in the x direction and net force in the y direction, setting them both equal to 0. This tells you how much you have to push to get the thing to go up the ramp. Look, sine of an angle is going to make for a small percentage of the weight. So that's what I'm saying. On a ramp, if I push it up the ramp, I can apply less force than if I lift the entire box. Generally, even with friction, this will be less force than lifting the box straight up. Of course, the problem is